Thank you, John. Yeah, welcome back to the final two lectures for today. So I will continue with my third part, which discusses the canonical quantization of constrained systems. So this morning we discussed what constrained systems are and how we can go to the Hamiltonian formulation. We applied this to general relativity in a certain choice of variables, and are now ready to basically apply canonical quantization. And this will be the part 3. And as this morning, I would like to pick you up from something you know. So we started with classical mechanics in the case of constrained systems. So before I go to full GR, let's also discuss a little bit what canonical quantization means in quantum mechanics that you're all familiar with. And also there, in the Hamiltonian formulation, we start with a classical phase space described by some set of configuration variables and conjugate momenta. And as you know from your lectures, what we are considering then is the so-called Heisenberg algebra, so a Poisson algebra among the configuration variables and momenta, which has these canonical Poisson brackets. So Poisson brackets among configuration variables vanish, similar for two including momenta. And since we are in a finite system, the Poisson bracket between configuration variables and momenta just gives Kronecker deltas. And we restrict, let's say, to 3 dimensions here. Now, given that already defines our model, and we want to derive the corresponding quantum theory. And for any other quantum model or quantum theory that you would like to describe, this is the first choice. You have to choose the classical model in a certain set of variables, which we have done here. Now we want to quantize this, and what we usually do is giving the classical choice. Before we speak about Hilbert spaces and operators acting on functions in these Hilbert spaces, there is a second step involved where we promote these classical relations to some abstract operator algebra. And we can understand this by considering an algebra, which is just a vector space equipped with an additional product. So you can take 2 elements from the algebra, multiply them, and you get again an element in the algebra. Now, remember from your quantum mechanics lecture, there was the notion of adjoint operators. And in order to be able to define this later in our Hilbert space, one has an additional structure, a so-called involution map, which I denoted by star here, which takes an element from our algebra. So for instance, the Heisenberg algebra maps it back to the algebra. And I just denote the image of this map by a star. And this has certain properties. It's linear. Here in this, if we take a linear combination of complex coefficients here of algebra elements, then we just get the adjoint multiplied by the corresponding complex numbers here. And similarly, if we, in an algebra, we can take a product. So if we apply the adjoint map, the involution map to a product, it switches the order and then is applied to the individual elements. Also, if we apply it twice, it's defined such that we get the same algebra element back. Now we want to do this for our Heisenberg algebra, which is generated by all Q's, all P's, and the identity in the algebra. We promote this to abstract operators. That's why I put heads on these quantities. And we want to quantize the classical model, so there should be a relation between commutators in this abstract operator algebra and the quantization indicated here by the head of the classical Poisson brackets with the usual AH bar factor. And similarly, we also want to relate the involution operation on these abstract operators to complex conjugation here. Now this you can do once you have the classical model. And then there is a third step, which means given this abstract operator algebra, you look for what we call representations. And this will give you then the Hilbert space and the operators acting on elements in the Hilbert space. So by such a representation, I mean a map, which I call pi here, which takes elements of these abstract operator algebra and maps them to the set of linear operators on some given Hilbert space. And with such a representation, this is always a map pi together with some Hilbert space on which these linear operators act. It also has certain properties. So it's, if I take a linear combination here of my operators, it should satisfy this condition so that the pi map is applied to A1 and A2 individually. Also, it must be compatible with the multiplication we have. So if we apply it to a product of A1 and A2, it should just be pi of A1 times pi of A2. And if we apply the representation to the image of the involution map, this should be represented by pi of A, and then we take the adjoint, and the adjoint is the adjoint in the Hilbert space here, which belongs to this representation. Now, if we go back to the Heisenberg algebra, these elements are Q hat, P hat, and the identity. And in order to implement this relation here on the top, we further require that our representation, if I apply it to Q and P's, and then consider the commutator of the two, it should be the same as I times H bar times the representation which corresponds to this classical Poisson bracket here, which is the identity times some Kronecker delta, which I forgot. So this is basically what we get here for the quantum theory. Now, there is a particular example of this that you're all familiar with, which is the Schrödinger representation that you use in quantum mechanics, where the Hilbert space is just given by the square integral functions over R3 here, if we work in 3 dimensions. And the pi map just maps my configuration variables or operators Qj here to multiplication operators in the position representation. And similarly for the momenta, they are mapped to derivative operators shown here on the right-hand side times I minus H bar. So that's something you're familiar with from quantum mechanics, where at least in my lecture, we didn't talk about representations and abstract operator algebras. I'm bringing this here because if you go beyond finite dimensional system and standard quantum mechanics, there's always the question whether representation exists, and if yes, whether they are unique. Because in quantum mechanics, you just use the Schrödinger representation, but there's an underlying reason for it, because it has been shown by Stone and von Neumann that if you require very weak assumptions on the algebra and the corresponding representation, then this is the unique representation up to unitary equivalence. If you have more complicated systems, such as field theories, and in particular general relativity is an example thereof, then the situation is usually not so simple. So in general, you have many, sometimes even infinitely many representations, and then you need additional assumptions to choose one, or additional motivations to choose one or the other. Now, if we have, for instance, 2 different representations, they can still describe the same physics. And we say that they are physically equivalent if we have a unitary map between the corresponding Hilbert spaces. So suppose we have 2 representations, pi1 and pi2, with associated Hilbert spaces h1 and h2. Then they are unitary equivalent if there exists a unitary operator mapping from h1 to h2, such that the represented operators here, pi of A, for instance, transform in this way. So in this sense, even if you have many representations, if they're all unitary equivalent, you would say they describe the same physics. But the generic case is that you have unitary inequivalent representations, and then in general, you can also get different predictions for the questions or situations or models that you are asking for. So we see the choice we have to make if we describe a quantum model is not only the classical algebra, but once this is chosen, we also have to decide in which representation we would like to work in. Okay, and this brings me to my next topic, but before I start, are there any questions on this? Seems not to be the case at the moment. So then let's move on to the topic of reduced quantization and Dirac quantization. So if you have an unconstrained system, as you're familiar with from quantum mechanics, you were just applying, or you will just apply the procedure which I was just discussing, but we know in general there might be constraints in our system, and then things become more complicated because we have in principle two different ways to deal with the constraints if we want to go to the quantum level. The first option is the so-called reduced phase-space quantization. And in this approach, what you do is you reduce the constraints at the classical level. So which means you solve all constraints at the classical level, and then you get a reduced phase space, which is, if you solve really all constraints, the physical phase space. And then you quantize only this phase space. And as we saw in the morning, we can have second class and first class constraints. And the second class constraints we reduce by introducing the corresponding Dirac bracket, which I was introducing in the morning, which is a modification, a generalization of the Poisson bracket. And if you do this, you can set all second class constraints strongly to 0. Now you might have remaining first class constraints in the system, and you still want to solve also with respect to them. And this you can do by finding suitable functions, which we call Dirac observables, which have the property that they commute with all first-class constraints. And remember, we said the first-class constraints generate gauge transformations. So this condition, in a sense, means we are looking for gauge invariant objects, which then encode the physics of the model. Already here, when you introduce the Dirac bracket, in general, the algebra will change. So if we go back to this simple Heisenberg algebra here, it's maybe even here, classical. These are canonical Poisson brackets. And we know how to quantize this. You saw this in the Schrödinger representation, just by multiplication operators and momentum derivative operators. Now, if we have a more complicated algebra, it might not work that you just choose Q to be a multiplication and P to be a derivative operator. Yeah? So if you modify the algebra, you make usually your life more complicated because you need to find representations of an algebra where there might be complicated phase-space functions on the right-hand side. Secondly, also here, when you look at the gauge invariant part of the theory, this algebra of the observables is in general more complicated as the algebra of the original kinematical phase space. Therefore, in these two steps, it might be the case that the algebra is so complicated that you don't find representations, which means you cannot complete the quantization program. So if you do these steps, you usually do it in a way such that you avoid very complicated algebras. Now, given that, you can describe the dynamics of these gauge invariant quantities, how we do construct them. I will explain a little bit more in detail later. But you can write down then the Hamiltonian equations for these objects, which are given by a Poisson bracket with not the canonical Hamiltonian, but something which I call physical Hamiltonian, which is really a true Hamiltonian, non-vanishing on the physical sector of the theory. Now, the quantization step consists then of finding representations of the observable algebra. This gives you then a direct access to the physical Hilbert space if you find observables for all constraints. And then these observables are promoted to operators. And if the algebra is simple enough, for instance, these can be also multiplication operators for the configuration variables and derivation operators for the momenta. Then you can promote the dynamics to the quantum level, and what you would get here is rather the Heisenberg picture, where the operators evolve, and this would then be the analog of the classical equation. So that's what you would need to do for a reduced quantization, and I will explain later how we can do this in the case of general relativity. Now the other approach goes back to Dirac, and because his motivation to introduce a compatible approach in a sense was that sometimes it's quite hard to solve all constraints at the classical level, and GR is one example where this is the case. And therefore, in Dirac quantization, you rather take the opposite approach. So you want to solve the constraints not classically, but in the quantum theory. And the motivation is that the kinematical algebra of all Q's and P's satisfies often standard canonical Poisson brackets, which you can easily quantize. And then you move the problem of dealing with the constraints to the quantum theory. Which means if we then look for a representation of the kinematical phase space, we don't get directly our physical Hilbert space, but we get an intermediate Hilbert space, which we call kinematical Hilbert space. Now, on this kinematical Hilbert space, you have operators for your elementary variables. So the constraints are function on phase space. So they are functions of these variables, which I called here Q and Pj. Now you can promote them to operators by using a function-preserving quantization and just define the operator to be the classical function evaluated at the operators. Since we saw, for instance, just a second, in general relativity, these constraints are quite complicated function on phase space. Of course, it's non-trivial to really define them. But if we are able to do that, suppose this is the case, then we select physical states by requiring that they are annihilated by all constraint operators, shown here. Now this yields a set of physical states, and given that, we can define an inner product on this set, and this yields then the physical Hilbert space. Do you have a question now? Then I stop, yeah?
My question is actually from your previous section, and it's that you said to derive dynamics, or to derive the Hamiltonian that generates the equation of motion, and we have the physical Hamiltonian. But what if we do not do that? What if we just use the Hamiltonian constraint to derive the dynamics? How would dynamics differ if it's just the constraint versus the physical?
Yeah, that's a good question. I will explain this a bit more in detail when we construct these observables. But you might remember from this morning that this observable is defined such that it commutes with all constraints. And we saw in general relativity that the canonical Hamiltonian just consists of constraints. So which means if I plug in the canonical Hamiltonian here, I get trivially weakly zero. Yeah, and you would see there is no evolution of gauge invariant quantities. This is the famous problem of time in GR. And that's why we need to work a little bit in order to define some dynamics which is non-trivially. But this can be done and will be explained later. Okay, and then I can also promote the condition on Dirac observables to the quantum theory, which would here mean that given a quantization of my observable O hat here, it has to commute in the quantum theory with all constraint operators for all I, defining the set which labels the different constraint operators. Okay, now we have first and second class constraints in the system in general, and there's a remark because we need to ask the question if we apply a Dirac quantization, whether this is consistent by applying successively constraint operators. So let's suppose we select physical states by assuming that they are annihilated by all our phi i's. There's a head missing here, and then we apply one constraint operator and afterwards another where I and j need not to be the same. So this is still vanishing according to this equation, so I can swap the order and take the difference. And then this yields just the commutator of constraint operators acting on physical states. And according to the definition of physical states, this still vanishes. Now, for first-class constraints, we learned this morning that they can be written as a linear combination of constraints again. So in the quantum theory, if I promote this relation to the quantum level, I would get the commutator here, and I would get a quantization of the right-hand side here. Now, if this is the case, for first-class constraint, it doesn't hold anymore for second-class constraint. Yeah? We had this example this morning where two second-class constraints were just equal to 2, which is not vanishing on the constraint surface. So this would mean in a quantum theory, it would be 2 times the identity operator, which means in general, this yields to contradiction for second-class constraints, because if we get, for instance, something proportional to the identity operator acting on a physical state, it would not vanish. So that's why Dirac quantization can only be applied to first-class constraints. However, if you want to promote constraints or want to solve constraints at the quantum level, there's a way out, in a sense, to deal with second-class constraints. Either you also introduce the Dirac bracket at the classical level and use this on the kinematical phase space, or as Francesca was already telling us in her talk today, there's also a notion of implementing constraints weakly, where you require that for each psi and psi prime here in the Hilbert space where this constraint is weakly satisfied, these matrix elements have to vanish. So both ways are possible, and also usually you do not do one or the other, but often you combine these two things. And I will also do this for general relativity. So I will solve the Gauss constraint using Dirac quantization, but I will discuss how the Hamiltonian and diffeomorphism constraint can be solved using reduced quantization. And also, as we will see in the part 5 of my lecture, where we discuss the dynamics, what you finally have to implement and techniques that you need to apply, they are not so different in the two approaches. And therefore, if you work in one direction or the other, usually it's beneficial in both ways, because you can learn something from either side and then get more insight by combining the two. Okay, since I will mainly apply reduced quantization in loop quantum gravity, I thought I'd give you a first simple example for Dirac quantization, so that you see how this works in principle. And again, I restrict to the finite dimensional case. So let's take a 2-dimensional classical system where we have configuration variables, which I denoted by x here. It was q in all the former slides. And we basically want to consider this. So j and k runs from 1 to 2 here. Now I just give you a primary Hamiltonian, which is given by a standard kinetic term here, plus some Lagrange multiplier and a primary constraint, which just tells us that the first momentum vanishes, where we have the standard kinetic term for the second. So obviously, because there is no x2 in the Hamiltonian, we already know that this primary constraint is stable, so this is the final set of constraints. Now we quantize the kinematical phase space here. It's a 2-dimensional system, so we just use square integrable functions over R2. And we can write down an inner product here, which gives us the norm squared of elements in this Hilbert space, which is just given by the integral over x1 and x2. And then here we have psi bar psi evaluated at x1 and x2. So this is the kinematical Hilbert space. Now we have to implement the constraint operator on this, which is simple because it's just a momentum operator. And we know how to quantize this. So we just use the standard Schrödinger representation, where we basically get that this is the partial derivative with respect to x1. Now the condition tells us that physical states are those which are annihilated by phi 1 hat. So if I carry this over, it means if I apply the partial derivative to my physical states, this basically has to vanish, and a solution is obviously that physical states are those which do not depend on x1, but only on x2. So now, and this is generically happen also in LQG, we can look whether these physical states are a subset of our kinematical Hilbert space. For the Gauss constraint, we will later see this is the case. But here, the constraint is an unbounded operator. So let's compute the norm of our physical states. These are states which depend only on x2. So we integrate, we take the inner product of the kinematical Hilbert space, compute the squared norm, and we see because the integral over x1 goes over the entire R range, this is definitely infinite, so the norm squared here will not be finite, and therefore these states are not square integrable. So there are no elements or no subset of our kinematical Hilbert space. But this is something which happens, and we can still describe those physical states, so the solutions of the constraints, as something more general, which are linear functions on our kinematical Hilbert space. Linear functionals, and this also is often sometimes called generalized eigenstates. So what are these linear functionals? So linear functionals are defined in this setup as a map which takes some element from the domain of our constraint operator. So this is just the momentum operator. So we know it's the space of Schwarz functions, and maps it to a complex number. So it takes some phi here of the dense domain and maps it to a fifth of phi, which is a complex number. Now, in order to write explicitly how this linear functional looks like, let me go from the constraint operator to its exponential, which is well defined in the case of the momentum operator. So let me introduce a unitary family of operators here, labeled by alpha. Alpha is some real number, and then I just take the exponential of my constraint, which is the momentum in one direction, so these are just translation operators. Now we can define the linear functional for each psi which lies in the dense domain of our constraint operators. Then the exponential can act on it. And we define this to be the integral over R over d alpha. And then we take the inner product of the kinematical Hilbert space and include the state psi here in the first entry of the inner product, and then u hat of alpha attached to it. So why do we do this in this way? We can now take an element phi and apply the linear functional to phi, and we will get something which is a complex number here, and if we perform the entire integral. Yeah? So the condition that phi is mapped to a complex number by the linear functional is satisfied. Now, given this, we carry over the condition on physical states, which was here for the infinitesimal constraint, that it has to be annihilated by the momentum operator. Now, if we consider finite translations, the analog condition is basically that it needs to be invariant under such finite transformations. And for this, I need to extend the action of the translations to linear functionals. So that's why I put a prime here. So u prime of some parameter beta acting on my linear functional, which I then apply to phi, is defined as the linear functional evaluated at the adjoint of u acting on phi. So why the adjoint is in this definition will become clear soon. Now carrying over the condition for physical states, we require for those that if we act with finite translations here on the linear functional, which is just given by the linear functional evaluated at U adjoint acting on phi, that this should be the original linear functional acting on phi, so invariant under this action. Now, if we compute this explicitly, let's just do it. We apply some U prime beta on L psi phys, and then evaluate it at phi. So we get this condition here. And this U alpha comes from the definition of the linear functional, and this U beta comes from this action on the linear functional. Now we can move that U dagger beta to the first slot. That's why the adjoint makes sense. And then we can use the properties of these translation operators, namely that the product here is the same as U of beta plus alpha. And then we can use the translation invariance of this measure here by just introducing shifting alpha by a constant, namely beta. And since we integrate over the entire range R, this doesn't change. And we can rewrite the second line here similar to the third line, which, apart from the twiddle on the alpha, which doesn't matter, is again the original linear functional L phys psi applied to phi. Yeah, so we have constructed objects linear functionals such that the constraints are implemented because these linear functionals are invariant under their finite action. So we see the general situation is that if we solve these quantum constraints, the solutions will not belong to our original Hilbert space, but to the dual. Okay, any questions so far before I move? Yes?
You were writing before in your slides about ordering the ordering of the when you transfer from classical expressions to quantum expression, there is this ordering problem sort of. So how do we choose properly the expressions from the classical to the quantum theory?
So you can only choose this in a sense properly or uniquely if you have linear dependence on these operators. So for instance, if you quantize using the standard model, you basically have linear combinations of annihilation and creation operators. Yeah? So there is no question. If you have phase-based functions which have products of Q and P to some higher order, you always run into this problem that you have ordering ambiguities. And in principle, each ordering is equally justified. And then you could just choose one and have sometimes physical motivation for choosing one or the other. But in principle, such a formalism does not tell you what operator ordering to choose. That's really an assumption of the model that you're considering. And often people take different orderings and see whether this has some kind of physical implications to choose one or the other. But this always occurs if you have higher order polynomials of mixed configuration and momentum variables.
So the subspace of the Hilbert space that satisfies this, each of these constraints that we chose will be different subspace in the Hilbert space.
So I mean, in this example, we had no ordering issue because it was just linear. So the operator that you choose once you quantize the constraint is fixed, and then you would derive the physical phase space. And then you would need to check in which way it depends on the ordering. Yeah. But since these are usually H-bar corrections, the semi-classical limit would be the same for all possible choices.
Okay, thank you.
Okay, now I would like to apply this to general relativity. And in order to apply a reduced quantization in LQG, we have to construct these observables I was mentioning before. So I will take GR in Ashtekar-Barbero variables as my starting point, which means we have the Azteca-Barbero connection, with label beta here, and its conjugate momenta, which are the densitized triads. And from this morning, we know we have this set of constraints, the SU2 gauge constraint, which I said I will ignore for the reduced quantization because it can be very simply solved in the quantum theory. So let's forget about this constraint for a moment. And I would like to get the reduced phase space with respect to the Hamiltonian and diffeomorphism constraint. Now, as you remember, these were quite complicated function on phase space. So if I have now the condition that I need to construct quantities which commute with the Hamiltonian as well as the diffeomorphism constraint, that's a complicated condition in the case of GR. And therefore, it's often, or therefore a motivation to introduce Dirac quantization at all was exactly the fact that it's not so easy to construct these classical quantities. Now, formalism in which such observables can be constructed in a systematic manner, which was introduced by Carlo Rovelli originally, is the idea to consider the dynamics and the way how we think about gauge invariant quantities in a relational manner. So the situation we have is that we have a certain set of variables and we need to construct gauge invariant quantities out of this. And the relational formalism basically allows you to split your phase space into two parts. One phase part is the set of quantities that you want to make gauge invariant. And the second part is a set which is a dynamical reference frame. And then you describe everything in relation to this dynamical reference frame. And this goes back to the question that you already asked earlier. This is a way, especially in general relativity, to circumvent the problem of time, because I was already explaining that the canonical Hamiltonian has this, is just a linear combination of the constraints that our model defines. And therefore, if we now consider the evolution of a gauge invariant Dirac observable, we would trivially get that any derivative with respect to t generating evolution by the canonical Hamiltonian will vanish. And this is, of course, not what we see in experiment. We have, for instance, in cosmology, non-trivial evolution. Now, the way to circumvent this problem here is to do not consider these t, which is associated to the canonical Hamiltonian, as a real physical temporal coordinate in which evolution is described, but define the parameter in which you want to describe the evolution of the gauge invariant quantities in terms of a dynamical reference frame. And as I said, in this canonical formulation, it would be some subset on your phase space, for instance, some fields. And then you describe the evolution of the remaining fields in terms of this reference frame. And the relational formalism basically tells us a technical way how to introduce this kind of physical picture. And it will also tell us, once we choose such a dynamical reference frame, how we can basically derive the generator of their dynamics, so this physical Hamiltonian, which I had in the Poisson bracket a few slides before. Now, let me just describe how we introduce this reference frame technically, and then I will tell you in an example of a particular reference frame for GR. So as I said, we want to reduce with respect to Hamiltonian and diffeomorphism constraint, and we want to construct observables relating to geometry, so relating to the Azteca-Barbero connection and the densitized triad. And as I said, I will drop the beta label now, at least I wrote it on my slides just for simplicity, because the notation will anyway be a bit complicated in terms of these observables. So then I have a second set of configuration variables for my reference frame. I need to introduce one reference field for each constraint, so 4 in this case, and the canonical momenta. Now I construct again a matrix Mij, which consists of all Poisson brackets among these reference fields and the constraints. And I say that reference frames which are suitable for this kind of construction need to be such that I can construct the inverse of this matrix. Yeah, and we are in field theory, so this matrix depends on x and y. And the inverse, by this I mean that if I integrate here over z and z prime, over this combination of m and its inverse, I get a Kronecker delta here for the matrix indices and a delta function in x and y. Now, given this inverse matrix, I can use a linear combination generalized to field theory of my original constraints, multiplied or contracted here with the inverse matrix, which gives me a new set of constraints, C prime, which is equivalent to the original set because the inverse exists, which means that the determinant of the matrix here is non-vanishing. So I'm multiplying the constraints by a non-vanishing object, by a non-vanishing quantity, therefore it defines the same constraint surface. This has the effect that if I consider now the Poisson bracket of the prime constraints with my reference fields, that these are canonically conjugated at least weakly. And weakly because we have this M here, which in general is phase-space dependent, which would also yield contribution in the Poisson bracket, but then I pull out the constraint and that part weakly vanishes. So further, it has the effect that this constraint, Poisson algebra of the prime constraint is weakly abelian, which means that, this weakly commute, which was not the case before. Remember, we had these structure constant or structure functions. Now the idea is, let's take these reference fields and construct gauge invariant quantities of A and E. And this will be done in the following way. A and E transform under gauge transformations, as well does the reference field. But you can compensate the transformations of A and E by choosing suitable powers of the reference field with certain coefficients. And this is shown here in the formula below. It gives me, for a generic phase-space function, which I denoted f, with respect to a chosen reference frame, which I denoted here by t, the gauge invariant version of f, which I can get by taking the sum from 0 to infinity, 1 over n squared. Then in nth order, I have n integrals over these arguments here of g, and g is up to some parameter tau, just the reference fields, and these tau are basically showing up here as arguments, so tau is the 0 constraint and sigma is for the diffuse constraint. Now we have nth power of these g's weighted by the nested Poisson bracket of f with n constraints. Yeah, and this is an expression, if you go to all orders, this will be gauge invariant in the sense that it commutes with all CIs by construction. So given these reference fields, you can construct the GIs and then the powers of the GIs and the nested Poisson brackets. The interpretation of this formula is that it gives me the value of f when my reference fields take the value tau and sigma. Yeah? So we have 4, sigma are 3 values. So sigma has an index A running from 1 to 3, and tau is the temporal physical coordinate, if you like, and sigma the spatial one. So now let's maybe look at the first 2 orders to give you an idea how this formula works. In 0th order, we just have the original function. In first order, we have the function plus a term which is linear in the GIs, and then we have no nested Poisson brackets, but just the Poisson bracket with f and ci prime. Now, in order to see that we can construct observables in this way, let's just take these 2 orders, truncate, and compute the Poisson bracket with Cj. Yeah? So I take 0th order, first order, and want to compute the Poisson bracket with Cj. This gives me two contributions, one where F just has Poisson bracket with Cj, and then where the second term here in the first entry speaks to Cj. Now, because Cj and Gi are non-trivial, but since Gi is more or less just minus Ti, we know that this gives me, again, my M matrix with a minus sign in this case. And so we just plug this in here. And then we just take the second part here where we have a nested Poisson bracket between F and two C's. So one C prime and the C which comes from the second slot here in the Poisson bracket. Now just copy the zeros order. In linear order, we rewrite the C prime in terms of C, which gives me an M inverse here from this relation. And the structure is such that the contraction here of M and M inverse works. So, and there is another contribution where we basically have the Poisson bracket of M with F, but since we pull out a constraint here, this weakly vanishes. And then we have the nested Poisson bracket in the last line. Now applying that M and M inverse gives the delta function, we basically get this Poisson bracket here. We get F and Cj here by performing the final integral. So these two exactly cancel. And we are left with this final term here, which includes two nested Poisson brackets. However, we truncated at linear order. So what you see is that the gauge transformation of the zeros order of F, which is this here, the infinitesimal one, is compensated by one term in the linear order, the one that cancels here. Now there is something left, which is a nested Poisson bracket. This would be cancelled by a term which is of order n equal to 2. So you see, if we go back to this exponential series here, you need really all orders in order to construct a gauge invariant quantity such that no final term remains here. And we also saw that it was very crucial that the reference field and the constraint satisfies this condition here, and that this M matrix is, for instance, non-vanishing here. So we realized this is a way to construct gauge invariant quantities once we have such a reference frame. So what are the properties? So it's a Dirac observable. I briefly sketched this for the first two orders, but if you take any order, everything will cancel, which means that our observable weakly vanishes. If we take the Poisson bracket with all constraints, and then we would take an independent set of these observables as the set which parameterizes our physical phase space. Now, what is interesting for us if we think about quantization is the observable algebra, which means if we consider now the Poisson bracket of two observables, it will not just satisfy the standard kinematical Poisson algebra in general, but one can show that weakly it's the same as considering the Dirac bracket of F and G. So that could be non-trivial compared to the Poisson bracket. There could be additional contributions here. And then you apply the observable map, and you get something here on the right-hand side, which can be, in general, quite complicated. So the Dirac bracket in this notation has this form because I defined the M slightly differently. So if you compare to what we had this morning, this is consistent if you define the Dirac bracket in terms of the M, which I introduced here like this. Okay, now the question is, what reference frame to choose? So far, I constructed everything choosing a generic reference frame. But if we want to quantize GR, we have to be a bit more explicit. And I would like to tell you a little bit a particular example for such a reference frame, which goes back to Brown and Kukash, where they applied this in classical GR and then quantized in terms of ADM variables. which is an action for additional fields coupled to general relativity. It's a so-called dust action, which is shown here. So it includes, in addition, 8 fields. So you have some scalar fields, some rho here. You have a 4 velocity u alpha, which is parameterized by 6 fields. One field is t. Then we have wj. J runs from 1 to 3. So it's an internal index here labeling the dust fields as j. So these are 6. And then you have the 7th t. And then we have another scalar field rho sitting here in the action. Now, if you consider now the coupled action of Einstein-Hilbert and this dust action, it turns out it's a system which has second-class constraints. So these second-class constraints can be solved by introducing the Dirac bracket. And if you do this, you get an interpretation of this rho here, which is just the energy density of the dust. And these wj fields included here are related to the momenta of t and sj. Yeah? So they are not independent, but you can express them in terms of the remaining variables, which are t, sj, and its momenta. So therefore, after reducing the second-class constraints, we end up with 4 independent dust fields, which I call t and sj here. So 4 fields, which is sufficient to choose as a reference frame for the Hamiltonian and diffeomorphism constraint. So in the notation from before, T would be T naught for the Hamiltonian constraint, and Tj would be the reference frame for the spatial diffeomorphism constraint. So U alpha satisfies here a geodesic condition from this action, so you can understand adding this dust as coupling observer dynamically to general relativity, which is free falling. So now let's consider the idea of these Brown-Kukash models. So we introduce canonical conjugate momenta, we perform the 3+1 split, we do the constraint analysis, and as I told you already this morning, when we add meta, we still get a Hamiltonian and diffeomorphism constraint, here labeled by total, which consists of the geometric contribution coming from gravity, C and Ca, plus some contributions from the dust, which are shown here below. But the explicit form is not so important for what I would like to tell you now. Now we consider this, and the idea of this model is that given this combination of constraints, we would like to make them weakly abelian, as we have seen that we can do this by introducing a reference frame. And here we do this by solving for the momenta of the dust. So we can write down an equivalent set of constraints, yeah, similar to the C prime we had before, such that the Hamiltonian constraint is linearly in the momentum of the temporal reference field, and the diffeomorphism constraints, here labeled by J, are linearly in the momenta Pj. Now the additional function here in the Hamiltonian constraint just depends on the Arsteca-Barbero variables, whereas for the diffeomorphism constraint it's a bit more complicated because also the dust fields enter. And the explicit form of these H and Hj functions are shown here. So these will become more important when we discuss the dynamics. Now, because these functions are linearly in the momenta, one can show that indeed, in this case, they're even strongly abelian. So you have rewritten the set of constraints relevant for GR coupled to dust in a way such that the algebra is strongly abelian. Now, how do we construct the Dirac observables now? We take T and Sj as our reference fields. This condition is satisfied that they are canonically conjugate to the constraints just by construction. You see they are linearly in the dust momenta, and everything else does not depend on the dust momenta, so only those contribute, and then you have canonical Poisson brackets. So now if we introduce the C primes here, because this has just the delta function, you see in this case C prime j and C are identical as expected because these C twiddle constraints I introduced, there are already a billion. So next we can construct Dirac observables, just applying the formula I was showing you before. So now we do this by introducing a G for the Hamiltonian and a G for the diffeomorphism constraint with parameters tau and sigma, apply this formula, and then get the corresponding observables associated to our Azteca-Barbero variables. So which I just call OA and OE, and the explicit form is these infinite power series, which I don't display here. But it's the same idea as I discussed before. Now, the nice thing is, and that's why coupling matter as reference frames is convenient as far as the later quantization is considered. If we now look at the algebra, and we go back to the relation I was showing you a few slides before, namely that the algebra of two observables is weakly the observable of the Dirac bracket. Let's apply this in the case of the Brown-Kukash model. Then first of all, we have a strong equality here. And secondly, if we compute the Dirac bracket, you realize in that model, because the reference fields are the canonical variables, the configuration variables of the dust, the Dirac bracket is identical to the Poisson bracket of A and E, which is just a delta function and some Kronecker deltas. This is constant on phase space, so if we apply the observable map, only the zeroth order will contribute, and we just get a delta function here in sigma and sigma prime, where these sigma and sigma prime are the coordinates in the physical spatial dust manifold. So we see that if we now want to quantize, the situation is as simple as for the original kinematical algebra, because we also get standard Poisson brackets. And the same holds, of course, also if I choose A and A or E and E, they all vanish. So which means now if we want to quantize, we have to look at the dynamics, and this physical Hamiltonian can be shown to be the observable, so the integral over all spatial physical coordinates, which I call sigma, over the dust space, which I call curly A's, of this Hamiltonian density. And this Hamiltonian density turns out to be exactly the observable associated to this lowercase h function, which I have here. And if I write this down explicitly, it's a square root. So it's a square root Hamiltonian where we have the observable squared associated to the geometric part of the Hamiltonian constraint, and then a certain combination, including the observable of the inverse metric of the geometric contribution to the diffeomorphism constraint. Now, since this includes only the geometric contribution, these will not vanish individually on the constraint hypersurface, and therefore we know that the physical Hamiltonian does not vanish. And this brings me to my final point, because my time is up. But I managed to basically tell you what the classical setup is in such a reduced approach. So we were able to construct these Dirac observables. And now in the next lecture, we will apply a loop quantum gravity quantization to this reduced phase space, and getting then operator for this physical Hamiltonian, as well as operators for the elementary Dirac observables of the Azteca-Barbero connection and its conjugate momenta. Thank you very much.